All right. Thank you. So thank you, Karthik. Uh, Now recording has started. All right. So what we are going to do is when we use 1 unit of electricity, what is the cost of fuel? Right? We are only looking at the cost of fuel, but in addition to this, there are other costs that these electricity companies have to bear. So obviously, the actual cost that we pay will be more than just the cost of the fuel. Second thing, we will look at the environmental impact. We will look at the environmental impact in terms of two things. One is the CO2 footprint, and second is the water footprint. Right? So CO2 footprint means how much CO2 is generated when we use 1 unit of electricity, and water footprint means how much water is used up when we generate 1 unit of or when we consume 1 unit of electricity, or when we generate 1 unit of electricity. So right now we are saying that there are no transmission losses. Whatever units are generated by the electrical company, all those units come to the consumer and they use that electricity. Right. So transmission losses, all these other losses we are not considering right now. Okay. So the way we generate electricity uh, is like this. So in your physics course, you must have heard about moving a conductor in a magnetic field. Do you remember that?
Yes, sir.
Okay, which law or what principle you call that? Hey, come on, yeah, 12th standard
Magnetic
physics.
flux.
Yeah. So if you have a
Magnetic flux.
magnetic field and you move a wire in a magnetic field, what happens in that wire?
EMF is
Current is
induced.
generated.
Current is generated, right? So that's how we produce electricity. We have a magnet, we have a magnetic field, and we move a copper wire through this magnetic field, and motion of that wire through that magnetic field generates electricity, and that's how that electricity is coming to us. Now obviously we won't be moving the wire with our hands. We will have a motor that will move the wire in the magnetic field, just like the fan that we have in our house. In the fan we pass a current, and there is a magnet inside that fan, and that causes rotation of the fan. So here we are going to do the reverse thing. We are going to rotate the wires or a coil inside a magnetic field, and that is going to generate electricity. So basic uh, 12 standard physics. So this motor is going to cause the motion of a coil inside this generator. Generator will have a magnetic field, say north pole and south pole, and then that will generate our electricity for us. Now the question is, how do I move the motor? So by motor we rotate by supplying high pressure superheated steam. So let's say this high pressure superheated steam is at 150 degrees centigrade. Sorry, not 150 degrees centigrade. It is at high pressure, 150 bar and 600 degrees centigrade. Recall the lecture related to steam table. What is the meaning of superheated? The temperature is more than the saturation temperature corresponding to 150 bar. So this steam, high pressure superheated steam, is going to rotate this motor. This motor we call by a different name. Motor, the word motor we use when I supply electricity and it causes motion of the impeller inside. when you supply steam, you call it as turbine. So there is a course in your second year called as energy engineering that's going to deal with different types of turbines, different types of generators, and so on. Okay. So we will not worry about that just now. We will only say that this superheated steam um, is supplied to this turbine that causes the turbine to rotate, just like you have a hydroelectric power plant, right? So there is a water that is flowing from a height that rotates the turbine, that rotates that rotates the armature inside the generator, and that's how it generates power. So instead of the water, it is a high pressure superheated steam. So this steam coming out of this generator, sorry, steam coming out of this turbine, steam doesn't come out of generator, steam comes out of turbine. This steam is now at low pressure. So let's say it is at 10 bar and it has lost its enthalpy also. So it is now, let's say, saturated steam. Okay. So the enthalpy difference between the high pressure steam and the saturated steam at 10 bar lower pressure, that enthalpy difference is what is given to the turbine. All right, do you agree? Do we is that okay? Let me just describe the problem, and then after that we will come to all the difficulties that we have. So now, how do we generate the superheated steam? Any thoughts about how we can generate superheated steam?
Shell and tube exchanger.
Shell and tube exchanger, okay, but what would be the heat source for generating this superheated steam?
So like the previous problem.
Correct.
Burn.
Like the previous problem, we burn fuel. So we have a furnace or a boiler, steam generator. So we supply fuel. Let's say we supply methane, 25 degrees centigrade. We supply air, excess air. What did we take last time? How much excess air did we take last time? Anybody recalls? 20% excess air. 20% excess air. We have a coil inside. That coil we supply water, and then that water picks up the heat and becomes high temperature superheated steam. In the previous problem, it just became a saturated steam at 130 degrees centigrade, right? Now we are going to design this furnace differently, and then we will get high pressure superheated steam. And then the flue gas that will come out. What temperature did we take the flue gas coming out last time? 200 degrees centigrade. 200 degrees centigrade. So this part is identical. You don't have to worry about this part. Now, this, what do we supply? What do we supply to the, so this is called as a boiler. Again, in your energy engineering course, you will see different types of boilers. How boilers are operated, what are the different types of boilers that you will see in your semester 4 energy engineering course. Okay, so what do we supply to this furnace in the coil? We supply liquid water. Do you remember that? Same as last time. Do you recall this problem? Yes, no?
Yes, sir.
Yes, sir.
Now, what will we do with this 10 bar saturated steam? What do we want to do with this 10 bar saturated steam? What do you think we will do?
So instead of supplying liquid water, we can send that steam only.
Right. So now that if you send the steam, then you will need to increase the pressure, right? From 10 bar to 150 bar, isn't it?
Yes, sir.
Right, so this is 10 bar. We will supply liquid water at 150 bar, isn't it? Which means we will need a compressor, and compressor will require same amount of power as the electricity. So then the power plant will not produce any electricity. Okay. So any other way you can think about? We need liquid water. How do you convert steam into liquid water?
Reducing the temperature or
How do you reduce the temperature?
compressing it.
How do you reduce the temperature? Compressor, we said, is out of question because it will use lot of power. It will use the same power as the electricity generated. Again, if we are just converting 150 bar 600 degrees into 10 bar saturated steam and again compressing it, it will require exactly the same power, right? In fact, more power, isn't it?
So
Second law
we
of
can use this. So we can use this saturated steam to heat up the methane and air.
correct. Yes, we can do that. Right now, let's say we are reducing the temperature and converting it to liquid water in a condenser. Excellent. Arya, good that you can use it to preheat this methane and preheat the air. Yes, absolutely right. Just let us make our life little simpler to start with. Then all these complications can be brought in. So we supply cooling water. So we supply cooling water which is at 30 degrees centigrade in a shell and tube exchanger. So let's say the cooling water flows on the tube side and this 10 bar saturated steam flows on the shell side, and the water picks up the heat from this saturated steam, gets heated up to, so cooling water now gets heated up to 50 degrees centigrade, and then we get water liquid water. So let's say this liquid water is now at 10 bar and it is saturated. Is that okay? Is everybody okay with this? That means it has just picked up the latent heat. This cooling water has just picked up the latent heat. Please stop me now if we have any doubts up to this point. If we have any doubts up to this point, can we go ahead? It is the same way that we have been doing evaporator kind of problems. We supplied saturated steam, it got converted into saturated water and it gave the heat for boiling of that salt solution. Same way here. Now, right now, it is not salt solution that we are boiling. We are just assuming that it goes to cooling water. Is that okay? Any difficulties so far? Any questions so far? Somebody need to say something.
So how does compression take place? Like, is it only possible by using electricity or any other forms are
No,
possible?
you can use the steam for compression, but point is if I want to go from here to here, I will need a compressor, isn't it? Don't you agree with that?
Yes, sir.
Right now,
Yes.
so now if I have to use compressor, suppose I am using electricity. Where is that electricity going to come from? That is going to come from whatever you are producing only, no?
Yes.
Now, if it is going from 150 bar 600 degrees centigrade to 10 bar saturated, and then 10 bar saturated is again going back to 600 degrees centigrade, don't you think it will require the same amount of electricity?
It would, sir.
It would
So
not.
that's why I was asking
Wait a second.
any
No,
other.
wait a second. No, it would not. Whether it is in the form of electricity or any other source of energy. This is one source of energy, isn't it? So imagine. So now, if you look at only this part, other people, if you are not having any doubt, just ignore what we are discussing. If you only look at this control volume, Arya, if you are looking only at this control volume, right? So I don't need this. It is just going round and round in circles, right? Isn't it?
Yes.
Yes or no?
Yes. Yes.
Right? So now if you think about this control volume, I am supplying energy for compression from 10 bar saturated steam to 150 bar 600 degrees centigrade, and I am generating electricity.
Equal amount would be needed to go
Equal
back.
amount. So is this not a perpetual motion machine?
Yes.
And would it be possible to operate this perpetual motion machine?
No.
No. And even if it was why? Because there are so many losses that are going to happen. So even if I wanted to operate a perpetual motion machine, I would require the same amount of energy that I generate. So the power plant will not generate any new energy for us to consume. Isn't it? Do you agree?
Yes. Understood. Understood.
Excellent. So we are talking about second law of thermodynamics now. Right? So when you do your thermodynamics course, all these things will come into picture. Now forget about all these. If you don't have this doubt, it is okay. You will get this doubt at some point of time. All right. Are you happy now?
Yes, sir.
Okay. Now can we go forward? So we supply 150 bar 600 degrees centigrade superheated steam. Okay. And we get out of this turbine 10 bar saturated steam. We condense this in a condenser and we get back 10 bar saturated water. Now what do you think we should do to this 10 bar saturated water? I want liquid water at 150 bar from this 10 bar saturated water. What should we do? Increase the pressure? Yes, no?
Yes. Yes.
Yes,
Yes,
sir.
sir.
Yes, sir.
Somebody respond, no? I feel as if I'm all alone talking. If I wanted to talk all alone, I could have talked in the middle of the night also all alone. It's very lonely. I'm lonely, right? So we do that in a something that we call as pump. So pump will increase the pressure from 10 bar saturated water to 150 bar. So again, energy would be required for this pump. Electrical energy would be required for this pump. But that electrical energy, we will calculate how much energy is required. We will calculate, but that energy required will be much less than how much electricity we are consuming, and that's how it produces the electricity. Right? Amount of electrical energy needed for a pump is much lower now than what has been produced in the plant. Okay? Because there is an additional heat sink that we have used, which is at 30 degrees centigrade. Okay. Now, what will we do with this cooling water? Cooling water which is at 50 degrees centigrade. What do you think we will do with that? Any thoughts about what we will do with this water which is at 50 degrees centigrade? Hey, come on, Brava, answer something. Otherwise, I will just share the talk and share the recorded, and you listen and do whatever. No, why we are meeting online?
Sir, we are thinking 1 minute.
Okay. What did we do with the cooling water? You see a hint on your screens? Anybody around? Anybody attending the class?
Yes, sir. Yes, sir.
Yes, sir.
Only Ariel seems to be attending. Nobody else is attending. What do you think we will do with this hot cooling water which is at 50 degrees centigrade? Do you see a hint on your screens?
Sir, we are lowering the temperature and humidifying the air.
Let me just keep on talking. If you have any doubts, you please ask. So we send it to a cooling tower where we supply ambient air. That ambient air gets heated up and humidified, hot humid air. And this cooling water which had become hot, it had become 50 degrees centigrade. Now it becomes 30 degrees centigrade again. What do you do with this now cooling water at 30 degrees centigrade?
We resend it back.
We resend it back. Excellent. But something happens in the cooling tower. What happens in the cooling tower? If I send 1 kg of hot water at 50 degrees centigrade, do I get back 1 kg of water at 30 degrees centigrade? Or I get something
No,
less?
sir. We get less amount of water.
Less amount of water. So in the cooling tower, let's assume how much water evaporates. We had calculated that. Go back to your notebooks. We had calculated how much water evaporates. Praveen, you are very quiet today. What happened?
No, sir, just I see. Sorry, sir.
How much water evaporates? If I have 1 kg of cooling water at 50 degrees centigrade, I send it to cooling tower. How much water are we getting at 30 degrees centigrade? Or 35 degrees centigrade, whatever is the problem. How much water we got back? If you have done this problem,
Sir, I've got around 970 grams.
970 grams, that means 2%. Ansh, correct?
Yes, sir.
2%. So 2% of incoming water gets evaporated and humidifies the air. Do you remember? Do you recall?
Yes, sir.
Yes, sir.
Right. So that means I need to add fresh water. you agree?
Yes, sir.
Right. So this is how a power plant produces power, and this is called as a Rankine cycle. You will do all these different kinds of cycles in your course on energy engineering. One of the simplest, one of the oldest cycles is Rankine cycle. Obviously, there are better ones now, uh, which use a lot of heat integration, but let's not worry about that just now. The steam goes in a closed cycle. This steam going in a closed cycle is called as Rankine cycle. Are you seeing that steam is going in a closed cycle?
Yes, sir.
We are not producing, we are not utilizing, or we are not generating any extra steam. Whatever water gets converted into steam gets again converted back into the steam and keeps on going around. And there is a separate source of heating, which is this fuel, methane and air, that gets burnt, and then that becomes the flue gas. Okay, and there's a separate water cycle, that is this black cycle, cooling water back, and then there is a fresh water. So if you think about this whole thing as a power plant, this whole thing as your control volume, if you think about this whole thing as a control volume, so this whole thing, suppose, is your now power plant. This yellow control volume, what is coming into this control volume? Methane. What is coming into this control volume is 20% excess air. Both are at 25 degrees centigrade. What goes out is fuel, flue gas, sorry, not fuel, flue gas. This is at 200 degrees centigrade. What is this flue gas going to contain? Carbon dioxide, oxygen, nitrogen, water, right? Because of the burning of methane. Okay, what else comes in? What else comes into this power plant? Ambient air.
Fresh water.
Correct. Ambient air, hot, humid air, okay, and fresh water. Which is used as a cooling water, and then that keeps on recycling, and we produce electricity. Do you realize? Do you realize this?
Yes, sir.
So
Yes, sir.
Yes.
how ambient air?
Ambient air. This cooling tower required ambient air, right? How did the cooling tower function? Cooling tower.
Yes.
uh,
Understood.
yeah. All right. So this is
Yes,
how
sir.
a power plant is working. So what we need to calculate is, for 1 unit of electricity, how much methane would be burnt? That is one. How much CO2 is generated? Water footprint, CO2 footprint, and how much fresh water would be required? Kgs of fresh water. All right. Do you agree?
Sir,
Yes.
sir, electricity is also required, no?
Oh, yeah. Thank you. Who's that? Who was saying that? Ohm, right? You said ohm,
Yes.
right?
Yes, sir.
Excellent. Yes. This small amount of electricity is required to operate this pump. Right? You will see that it is negligible. We will calculate, but we will see that it is negligible as compared to what is produced. Right? So you can find out how much electricity is required also for operating this pump. Right? Or we can say that this electricity is going to come from this electricity only, and so the net electricity that is produced. Okay, Om,
Yes, sir.
you understood now? The
Yes, sir.
electricity required for operating that pump is going to come from the electricity that is generated in the generator. So we will just say net electricity is produced. Okay, Om?
Yes, sir.
Okay. Shall we go forward? Shall we
Yes,
go
sir.
forward?
Yes, sir.
Yes.
Yeah, so now that we are using steam for these different purposes, I will use steam tables and we will get the enthalpy values of superheated steam 150 bar 600 degrees centigrade, 10 bar saturated steam. I need all that for doing enthalpy balance calculations, right? I need 10 bar saturated water, 150 bar and saturated temperature at 10 bar. Correspondingly, that much amount of enthalpy we need to is what comes in is what comes into this boiler, right? So I need enthalpy value. So let me just open steam table and then we will get enthalpy values from there, and then after that we will do the problem. Is that okay? Yes, no?
Yes, sir.
Yes, sir.
So
Yes,
just
sir.
so we have been using the saturated steam table right now all the while. Now we will one second. Second, let me open that steam table. I will show you what else is there in the steam table. So let me stop sharing this. Yeah, steam table is there. Okay, are you able to see the steam table?
Yes.
Okay.
Yes, sir.
So what we have been using is saturation temperature table and saturation pressure table for evaporator problem and for other problems that we have. Now we need to look at the superheated vapor, means superheated steam table. Okay, so let's go to page 15. Right, this is superheated vapor table. You agree with that? What was the pressure of the steam? 150 bar. 150 bar is how many megapascals?
So 15.
15 megapascal. Excellent. 15 megapascal. So this is 0.01 megapascal, 0.05 megapascal, 0.1 megapascal. Like that, we will need to go to 15 megapascals. This is 1 megapascal means 10 bar, 20 bar, 30 bar, Aha, 15 megapascal. Do you see? And what is the temperature? 600 degrees centigrade. Do you see this? Yes or no?
Yes, sir.
Yes,
Yes, sir.
Ah, so enthalpy is now here. Do you see? 3579.77 kilojoules per kg. Somebody note down this value. Yes, no.
Yes, sir. Noted.
Note it down.
Yes, sir.
Thank you. Let me also note down 3579.77 kilojoules per kg. Okay. Now we need 10 bar saturated steam coming out of the turbine. So 10 bar saturated steam. Now we have to go back to saturation pressure. Okay, 10 bar. This is saturation temperature table. This is saturation pressure table. Right, 10 bar. 10 bar means this is 100 kilopascal. There is 1 bar. This is 1000 kilopascal means, is it 10 bar?
Yes, sir.
Right. So 10 bar. What is the temperature correspondingly? 179.87. Somebody note down this. Approximately 180 degrees centigrade. What is the enthalpy of saturated steam? It is 2776.28. And after that condenser, we are going to get 10 bar saturated water. What is the enthalpy of that? 762.23. Do you agree? Do you disagree? Anybody thinks I am showing a magic trick and bringing out rabbits out of a hat? Anybody is following what we are talking? Yes, no?
yes, sir. Yes, sir.
Yes.
Yes, sir.
Okay.
Yes, sir.
Okay. Now after the pump, what are we going to get? We are going to get 150 bar water. But let's say that 150 bar water is also at the same temperature. There is hardly any change of temperature after the pump. So we have 150 bar and 180 degrees centigrade liquid water. Right. So this is now, it is now compressed liquid table. So let's go to page 25. Aha, compressed liquid table. Compressed liquid after the pump is at 150 bar, which means 15 megapascal. 15 megapascal. And it has a temperature of 180 degrees centigrade. That means it will have an enthalpy of 770.03. Do you see that?
Yes, sir.
Okay. Now can we go back to our problem? Anybody has any doubts? Anybody has seen the steam table? Anybody has downloaded the steam table?
Yes, sir. We have.
Yes, sir. I've done it.
Yes, sir.
Yes, sir.
3-4 people have downloaded out of 90 in the
Yes, sir.
class.
Yes, sir.
Yes, sir.
5, 6, 7, 8, 9, 10.
Yes, sir.
10 people out of 90, 11, 12, 13.
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
So whatever we did just now, do it for yourself in the steam table. So let's go back to our problem. Okay, so now whoever was noting down all these enthalpies, tell me the enthalpies. 150 bar, 600 degrees centigrade. What was the enthalpy?
3580.
3580. And let's just round off, right? So 3580 kilojoules per kg. 10 bar saturated steam, what was the enthalpy?
2776.
2776 kilojoules per kg. 10 bar saturated water, this is at 180 degrees centigrade.
762.
762.
180 degrees centigrade. 762 kilojoules per kg. Now this 150 bar and 180 degrees centigrade. What was
770.
this?
770.
Right, 770 kilojoules per kg. Now our problem is complete. Let me just give you couple of more sets of data. Assume that this turbine and generator combination has, let me write it here, turbine and generator has 80% efficiency. And let's also say that this pump also has 80% efficiency. What does efficiency mean? Efficiency, what does it mean?
Sir, whatever is given as
So
input,
the
how much
conversion
of
of
it is
one-
converted?
Right, whatever is the output from that equipment divided by whatever is the input to that equipment into 100, that's our efficiency. Now if you think about the turbine and generator, what is the output?
Electricity.
Electricity. This is the output from the turbine and generator put together. What is the input? Input is the difference between the enthalpy of superheated steam minus the enthalpy of saturated 110 bar steam. Do you realize that? This is how much energy we have put into that turbine. Yes, no?
Yes, sir.
So input is difference in enthalpy between superheated steam minus saturated steam. This is at 10 bar, this is at 150 bar and 600 degrees centigrade. This enthalpy difference is what is supplied as an input to the turbine to make that turbine rotate, which rotates a coil inside a generator, and that generates electricity as our output. Do you agree with that?
Yes, sir.
Pump. Now, what is the input for the pump? Input for the pump is our electricity.
Electricity.
What is the output for the pump? Output for the pump is the enthalpy difference between 150 bar, 180 degrees centigrade liquid water and 180 degrees centigrade 10 bar saturated water. Pump is increasing the pressure from 10 bar to 150 bar. So it has added enthalpy into that pump. That enthalpy difference between the 150 bar water and 10 bar water. Do you agree with that?
Yes.
Yes, sir.
Right. Okay. Now the problem is complete. Now can you find all these things? Cost of the fuel, cost of the CO2 burnt or CO2 generated, water footprint. Find out all these things now for yourself. What is our basis? The basis that we want to take is 1 unit of electricity that is generated by this plant. And remember, these plants are huge power plants. So 500 megawatt electric power plant or 1000 megawatt electric power plant, huge amounts of electricity generated. But we are doing a calculation for per unit of electricity. So let's assume that the basis is 1 unit of electricity that is generated here. Don't worry about the electricity that is consumed here just now. Don't worry about this. Assume that it is just 1 unit of electricity that is generated here. We will do that correction a little later. Okay, so solve.
Sir,
Is
I have
the
a question.
yes, Praveen.
So you gave the 80% efficiency of turbine and generator.
Huh.
So there the 80% is there separately or as a
The
combined system?
turbine and generator put together as one system,
They are combined.
as one. See, right? I have just shown you two. There are two actually. There are two, three other small things also in between. Bearings are there. Transmission powers are, transmission chain is there. Don't worry about all of these. So we are just saying turbine generator whole thing put together is a 1 unit, because they are really 1 unit. Turbine and generator are in the same housing, so to say. There are so
Okay,
many
sir.
other internals that are there. Let's not worry about that. You will come to do. You will do all that in your energy engineering course in semester 4. Okay, Praveen.
Yes, sir.
Okay, solve. If you have a question, just ask anytime. I am here only. I am not gone anywhere. Unlike some of the students who log in and disappear, I am here only. If you have any doubt, any point of time, just ask. Unmute yourself and ask. If you want, I will switch on the camera just to prove that I am here. Unlike what you do in your other lectures.
Sir, the excess air is also at 25 degrees Celsius, right?
Yeah. This is the same as last time.
Okay, sir.
I have just given the same values so that just to make your life a little less complicated, because it is the same thing that we used in our steam problem. 25 degrees centigrade, 20% excess air, flue gas at 200 degrees centigrade, exhaust going, gas going out. So all those enthalpy values you have already calculated. So that's why I gave the same values. Any answers so far?
No, sir.
Anybody would like to volunteer with their answers?
Excuse me, sir.
Yeah.
Sir, when we solved the boiler problem that day, then we considered that the output is saturated steam at 130.
Correct.
But
Correct.
how are we making it reach 600 in this
Yeah. Yeah.
problem?
So now the boiler design that is there for generating steam is different from boiler design that is intended to make a superheated steam. So the design part is different, just so that it makes a superheated steam. So you will learn about different types of boilers in your energy engineering course. Let's not go into that just now.
Okay, okay.
There are extra coils, extra something's called as economizer. So basically generates more heat from the flue gas.
Sir, in the condenser, the ambient air is bone dry.
Yeah, I mean, let's not do this cooling. In the condenser, there is no ambient air. In the cooling tower, we supply ambient air. In the condenser, we use cooling water. Hello.
Yes, sir. Yes, sir. In the cooling tower, are we supplying bone dry ambient air?
Yeah. So don't do this cooling tower problem now. We have already done it. Just assume that 2% of the incoming water evaporates, just so that we can find out how much fresh water is required.
Okay, sir.
Okay. Just decouple the cooling tower calculation. We've already done that. No point in doing it again. It was similar, 50 to 35 at that time it was. Now it is 50 to 30. And anyway, ambient air, I have not given you any data.
Okay, sir.
I just wanted you to recollect this cooling tower problem. So I drew it again. Just so that we know that about 2% of the incoming water is evaporating. And that much fresh water I have to make up. All right.
Yes, sir.
Any answers? Any answers?
Yes, sir.
Yeah. Would you like to volunteer and tell us how you have solved?
Yes, okay, sir.
Should we wait for some time for other people to finish, or
Sir, I'm also done with it.
Okay, sir.
other people please tell whether you need few more minutes or whether we can discuss?
So a few more minutes. Sir.
Okay, okay, Nishan. So after a few more minutes. Anybody stuck at any point of time? Anybody wants hints? Om, stuck anywhere? Om is not around.
Sir, I am around.
Oh, so I asked a question. Are you stuck anywhere? You need hints?
No, sir.
Anybody solving? Anybody knew that there is something to be solved? Nobody knows that there was something to be solved.
Yes, sir. Solving, sir.
Huh. Wow, 40 people are attending the class. Wonderful. Should we solve? Do you need more time?
Sir, can I tell the answer?
Okay, you want to tell the answers. Okay, tell the answers. I have no idea what the answers are. Well, I have actually. Yeah.
Sir, so the fuel used, the methane, is 0.35 kg.
Kgs of CH4. 0.345.
345.
Let's just say 35.
The same as Praveen, sir. 0.37, same as Praveen.
Okay. Thank you, Atharva. What else?
So I
Kgs
also
of
got
I'm
this
getting
too.
0.37.
Right.
Yes, sir. I got 0.37.
Okay. Kgs of CO2?
1.03.
Yes, sir, 1.03.
103.
Atharva 1.03. If your kgs of CO4 are and
Yes,
kgs of
1.03, sir.
CO2 has to be consistent with each other. So 0.37 has to correspond to 1.03. Okay. Water?
2.77 kg.
Let's just say 2.8.
So water is
Atharva?
3 kg, sir. 3 kg.
Yes, sir.
Yeah,
2.7.
2.73. They're all the same. So should we solve or everybody can solve? It's like I'm the only one talking to myself.
So we can solve a little more time, but till next lecture we can do
Or
the
okay,
rest of the people.
take your time. Okay, take your time. Solve till the next lecture. And anyway, the solution I will share as a separate video. Uh, so you can look at that solution as well. So just couple of things. Um, So how much electricity is used in the pump now?
Sir, 0.015 kilowatt hour.
Right. So electricity used in the pump. (0.015
Kilowatt hour.
kilowatt hour). Right. So out of the 1 unit that you are producing from the generator, 0.015, that is 1.5%, is used up in the pump. Right. So very, very small. Okay. That's how we are producing extra electricity. Any other answer for electricity used in the pump?
Yes, sir. Same.
Same.
Same, sir.
Yeah. So now do you see that how it is producing extra electricity? We have used up only 1.5% of what has been produced. Rest 98.5% is there for us to use. So every time, and so if you think about this 0.37 kgs of methane, let's say methane cost is some 30-40 rupees. So this itself comes to about rupees 10. Isn't it? If you take LPG, it will be more. If you take CNG, it will be about 15 rupees. Do you agree? Just the
Yes,
cost
sir.
of the fuel burnt. We are not even considering any other cost like maintenance, making all this equipment run properly. We are not considering the electricity losses, transmission losses. We are not considering any cost associated with any other activity. Just the fuel cost itself comes to rupees 10 per unit. Do you agree?
Yes.
Yes, sir.
Government is giving us at rupees 8. So government doing a good job, bad job?
Good job.
Well, of course, this 10 is a overestimate. This is overestimate. Why is it overestimate? Because this cooling water is extra thing that we are consuming, right? As Arya was suggesting, rather than condensing it using cooling water, we could have preheated the methane and we could have preheated the air and then used that to condense the steam and make it into liquid form. So their heat would not have been wasted. We would have required less amount of cooling water and we could have been better in terms of this cost. The amount of fuel used would have been lesser because we are using this heat along with this 10 bar saturated steam. We are using that heat partly to preheat these gases. So we would have used less amount of methane and therefore the cost would have been lesser. So obviously the cost that we have got is an overestimate because this is a very simplistic Rankine cycle that we have taken. In your energy engineering course, you will see many more such cycles which are better and better, which are more efficient than this Rankine cycle, so that the amount of fuel used is less, and therefore government is not doing such a good job at selling us at 8 rupees. Actually, they are doing a sort of a fairly okay kind of a job. It's not a great job also. It is not that they are fleecing also. All right, so couple of things I wanted you to think about. Whatever electricity has been used up, whatever electricity has been produced. Where is the source of that electricity? That source of that electricity is in the calorific value of the fuel. Okay. Now again, if you think about this overall plant, this overall plant, if you think about this overall plant, right, where was that? Where did we draw that plant? Overall plant we drew somewhere, right? Right, here. Right, this is the overall plant that we had drawn. This methane that we have used, the calorific value of that methane, calorific value of that methane, that has what has generated the electricity, that has what has converted the calorific value, heat of combustion, that has what has allowed us to generate steam, superheated steam, that is what allowed us to drive the turbine, that is what allowed us to generate the electricity. What was the calorific value last time we took in last time's problem? You remember the lower calorific value, 50 megajoules per kg, isn't it? Yes or no?
Yes, sir.
So calorific value was 50 megajoules per kg. And how much methane we have used? We have used, let's say, 0.37. Let's just make life, okay, let's just take 0.37. So how much energy we have got by combustion? Energy generated by combustion is 50 megajoules per kg, and we have used 0.37 kgs. Isn't it? What is the value? 50 multiplied by 0.37.
$18.5.
Great. Did you use? Yes or no?
Yes, sir.
Okay. 18.5 megajoules, which is 18.5 into 10 raised to 3, which is 18,500 kilojoules. Do you agree with this?
Yes, sir.
Yes. So now, this was the overall block diagram for the plant. This was the block diagram for the plant, right? We can construct, think about this as your plant. Can we construct sort of energy diagram, if you like? We have generated 18,500 kilojoules of energy by combustion. Where is that energy going? 18,500 kilojoules. Where is it going? Look at this yellow control volume. Look at the overall plant and tell me, where is that 18,500 kilojoules going?
It is going in the flue gas,
Correct.
electricity,
Correct.
and cooling.
Correct. It is going in the flue gas. It is going in the electricity produced. And it is going in this cooling water. Do you agree? This is where it is going. It is going out. If you think about this blue control volume, this is where the energy is going out in terms of flue gas, in terms of electricity produced, and in terms of cooling water. out of this 18,500 kilojoules, how much electricity we have produced? We have produced electricity of 3.6 into 10 raised to 6 joules, which means we have produced electricity corresponding to 3,600 kilojoules. Right? So this electricity produced out of this 18,500 is 3,600 kilojoules. How much energy is going in the flue gas and how much energy is going in the cooling water?
Almost 4/5.
Almost 450. Now, individually, how much is going in the flue gas and how much is going in the cooling water out of this 18,500? Nishant, Praveen, quickly tell me how much is going in cooling water?
Sir,
11,000.
11,000.
1100 or 11,000?
11,000.
11,000 kilojoules, right? And rest 3,400 or 3,400 kilojoules is going in this flue gas. Yes or no? Out of this 18,500 that has been generated, only 3,600 is going as electricity. A huge amount is going in this cooling water. So if you want to improve the energy efficiency of this power plant, we have to not use as much cooling water, and therefore what Arya was saying earlier, that don't use this cooling water, use it to preheat the methane and preheat the air, so that the energy wasted with the cooling water would be less and we would use less amount of methane. Arya, do you agree?
Yes, sir.
Your original suggestion was very good. We can take that because we wanted to see all these things. Okay, so now that we are coming to the end of the course, we should think about a global picture. We have done material balances, we have done energy balances for individual equipment. Now it's a time to look at a global picture. Try to look at what happens in terms of materials in the whole plant, what happens in the form of energy in the whole plant. And then once you figure out overall where your energy is getting lost, you can think about ways of improving the plant performance. Okay. Some of you may say that, don't use methane. So what could be alternate fuel sources? One could
Sir,
be
Windmills,
burn coal. Instead of using methane, burn coal or burn biomass. Okay. Don't burn trees, but whatever waste biomass is there from agricultural produce, burn that, generate electricity. Anybody from this Punjab, Haryana, Delhi side in your class? Nobody is from Punjab, Haryana, Delhi side.
no, sir.
Okay. Okay. Anyway, you are aware that in every day, every time, every year in winter, people talk about farmers burning the stubble that is there, leftover material in their plants, in their farms. Maybe
Yes,
somebody,
sir.
maybe somebody can, maybe somebody can take that and burn, as instead of burning it in a field, burn it as a fuel source in a power plant. and then that way it will reduce the problem of pollution and smog and fog that every year encompasses or eclipses these parts, and we might as well generate electricity from there. Any other source of energy that you can think of?
One suggestion: why
Yeah.
don't we use mechanical engines instead of a turbine? Like as we use in generators,
Mhm.
we supply fuel, and
Mhm.
it directly converts mechanical energy uh,
But that's how
into electrical
yeah, I
energy.
mean, whether it is separate, whether the combustion region is separate, or whether the combustion region is inside the turbine itself, like a car you are saying,
Yes, sir. Yes, sir.
right?
Like a car.
Right. So car is burning petrol, and it is running your wheels, and it is running your engine, and it is also generating electricity, which is charging the battery of the car. Only the starting time battery is used for starting the car, but rest of the time battery is not used, and whatever electricity that you use in your car for air conditioning, for playing music, for lights and all that, that is coming from battery. So battery is getting charged by the same time as you use the as you drive your car. So only thing that happens is, yes, the car engine would become so big, because think about how much power you are generating in your cars, whereas these power plants have to produce 500 megawatts of electricity or 1000 megawatts of electricity. So think about how big that engine would be, and making such a huge engine to generate this much amount of mechanical power, it is much more easier and convenient for construction as well as maintenance to generate steam and let the steam drive a turbine. Right? It's okay for a car to have the fuel directly go to mechanical power. It is inconvenient to do it in a power plant because of the huge amounts of energy that are generated. All right, Arya?
Yes, sir.
Uh, any other source of energy that you can think of?
Sir, solar.
I mean, okay, because other alternate sources we are not talking about. Solar, hydro, wind, tidal, all those dot we are not talking about. Any other source which generates energy, like burning of coal, or like burning of methane, or like burning of biomass? Any other?
Sir, waste plastics.
Right, okay, so biomass, waste, plastic, fine. Okay, any other source? Anybody likes Einstein?
So nuclear energy.
Nuclear, right? So use nuclear fuels. They generate electricity by fission. Can you rework this whole problem, that instead of methane being burnt, it is coal being burnt, or biomass being burnt, or waste plastic being burnt, or uranium fissile material being undergoing fission and generating heat, thereby generating steam? For all these cases, can you think about cost? Can you think about kgs of CO2? Can you think about kgs of water used up? Can you calculate? Or if you go to alternate sources, solar, hydro, wind, tidal, what is the cost? What is the environmental impact? Environmental impact may not be in terms of carbon dioxide. If it's a hydroelectric power, environmental impact could be in terms of building big dams, submerging the land around, which could have been used for farming, which could have been used for people to stay. If it is wind, if it is tidal, what could be the environmental impact? What could be the cost? What kind of hardware is required?
Sir, but it wouldn't be a constant source if it is solar, wind,
Right,
or
great,
tidal.
correct. So good point. So solar is not a constant source. It is available only maybe 8 hours, 9 hours, 10 hours in a day, and that too in a rainy season, even lesser times during the day. So, and same way with hydro, or same way with not same way with wind, or same way with tidal energy, it may not be available throughout the day, night. So along with this, you need some kind of storage. So let's say if it's a solar power plant, then you are generating a lot more energy. You store that energy, and during the night you supply that stored energy to everybody. So batteries, what could be, that is one way of storing energy. What could be other ways of storing energy? So as we are coming to the close of the semester, these are the things that I wanted you to think about. What is the cost? What is the environmental impact? What kind of hardware is required? And storage. What kind of storage would I require? How will I store energy? Batteries is one form. So lithium batteries, sodium batteries. What could be other forms of batteries that we would want to store? Right? So energy in general, energy engineering is a big field, and there is plenty of scope for doing new things in that. You could think about different ways of generating electricity, different ways of utilizing the power, different ways of storage. Right. So let's stop here for the day, and you can solve now. Let me stop presenting. Let me stop recording.